This week we will discuss concentration inequalities. Concentration inequalities are very important to understand sample complexity for many machine learning algorithms. Let's consider these two questions. The first question is, suppose that x1 through xn are IID random variables, so we obtain n different random values that generated from a given distribution. Then can we say the error bound of the empirical estimator, which means 1 over n times summation over I1 to n xi to the true average. So what is the difference between 1 over n summation I1 to n xi minus the true expectation value? Essentially, from the law of large number, we know that this value will converge to the expectation with high probability as n go to infinity. This value will go to this expected value, the true average. But for finite n, so if n is not infinity but some finite value, there is definitely some error. We cannot obtain the exact value of the true mean, true average. Instead, we have some noisy version of true average. The empirical average is not exact the expectation value, but some estimator with some error. Okay, so with concentration inequality, we can understand this error bound as a function of n. Okay, so as n go to infinity, what is the speed of convergence go to this expectation? We can answer for that question and we can describe the convergence speed using concentration inequality. The second question is this. A classification algorithm has an error probability epsilon. In other words, the output of the algorithm is classifies or randomly sampled data with probability epsilon. Suppose that. Then what is the probability of the event that the algorithm misclassifies more than 200 times epsilon data point among 100 data points? Okay. On average, we will have 100 times epsilon error data point. This is in expectation. Why? We have epsilon error rate and we have 100 sample data point. So on average, we have 100 times epsilon number of misclassified data point. But the random realization always has some error. So we can have more error or we can have less error. So using concentration inequality, we can say that the probability for the events that our observation is extremely bad, such that the number of misclassified data points much bigger than 100 times epsilon, so even bigger than 200 times epsilon. Using concentration inequality, we can say the probability for this kind of event. So these two questions are very crucial to explain sample complexity for machine learning algorithm. So here sample complexity means so how many data points do we need to guarantee some target performance of our algorithm? To understand such sample complexity, we need understand concentration inequality.